I think we can start. Yes? All right. So we are very, very happy to be invited to give a guest lecture here at this top university in Hanoi, Vietnam. I say we. Yeah, this is my colleague Dieter. Yes. My name is Wouter. I know it's difficult to pronounce maybe. If you think of a bottle of water. Yes, so yeah, that's pronunciation is already very close to what it should be. Okay, yes. So a big welcome. The idea for this afternoon, or I think it will take about 2 hours, is let us first present the university where we work, yeah, because we're setting up some cooperations with your university here. So we'll discuss this in about maybe 5 to 10 minutes, and maybe listen carefully, there might be opportunities for you as well. Yes? And then we'll talk about AI, and that's what you're here for. Like the first part, it will take about 1 hour, I guess, is more of an introduction to general concepts of AI and generative AI. Yes? So I don't know what is your background. Some might already have some prior knowledge to AI, to deep learning, and to other types of AI models. I heard it can be like a mixed group, so some have prior knowledge, others don't. Yeah? So I hope if you have prior knowledge that it will still learn something new, that there might be some overlap with what you already know, but okay. And if you're completely new to AI, I hope it might inspire you and to get some more understanding of some general concepts. Yeah? That's for the first part. Then my colleague Dieter will give the session at the second session, and that will build on top of my first session here, but will be more technical. Yeah, it will be more about how you can start from text, change, modify, transform this text into meaningful, what we call embeddings, and then these embeddings can be given to an AI model to produce some useful output. So that part will be more technical. Nevertheless, there will be a lot of demos, Dieter, so in that sense it will not be that boring, of course, yeah, but it will be interesting, but just keep in mind it might be a bit more technical. Good? Yes? If you have questions, if you want to share something with the group, or if you want to give a remark or whatever, don't hesitate to interrupt me. Okay? Good? Agreed? All right. So Dieter and I, we are basically coming from a Belgian university, a technical university called Howest. Yeah. And I don't know who knows Belgium. Who, if I would show the world map, who would be able to pinpoint Belgium? Okay. Then I will jump ahead to here. This you recognize? Like Europe? Yes? France, Spain, Germany, Great Britain, and so on. And here, actually in the center of Europe, you have this tiny country called Belgium. Yes? Very small, like this. The maximum distance is about 320 kilometers. In a straight line, you can travel. Yeah. Nevertheless, it's quite interesting to study over there because everything is very close, very nearby. For example, if you study at our university, in maybe 2 hours you'll be in Paris, in France. In maybe 1 hour and a half you can go to London, you can go to Berlin, to Amsterdam, and so on. And, yeah, of course, and many nice cities in Belgium as well. And so, in that sense, it's quite interesting to study over there. very quick information about our university. Actually, we're quite a small university. Talking about 12,000 to 12,000 students spread over 2 campuses. So we're a small university, but the biggest in IT in Belgium. Yeah, so when it comes to IT, AI, and these computer science related topics, we are the biggest in Belgium. Yes? Okay. In Belgium, any idea what languages we speak there? So, the northern part we speak Dutch. It's not German, yeah? Dutch. Yeah. Southern part we speak French. And then in Brussels we speak all type of languages, and a small part they speak German. Yeah. But actually everybody speaks English, so if you would come study in Belgium, English will be more than enough. It will be more than sufficient. We have some beautiful cities, like maybe Bruges, one of them, Ghent, Brussels, and so on, and very close to other capitals in Europe. Yeah. I think most of you study in, let's say, AI or AI-related program. Is that correct? Computer science, AI? Yes? Okay. Then I think we might have something that can be interesting to you. This is a 3-year program. I'm not sure if it's really visible. No. Yes? Full screen, yeah. Okay. Oh, no. Yeah, it's or maybe I can just zoom in a little bit. Ah, no, yeah. Oof. Yeah, like this maybe. Already a bit better. Yes. This is an international program we offer. Yes. So for this program we have students coming from all over the world. Go from South America to, of course, Europe and neighboring countries, but also Southeast Asia and so on. So it's open to everyone. Yes, it's a 3-year English taught program focusing on AI. Yeah? And what is interesting, only the first semester we give some, let's say, basic courses like a bit of mathematics, some programming and so on. Yeah? But from then on, the entire program is focused on AI. Yes? And our idea is not to give you so much theory. What we expect you to do is to be able to solve practical problems with AI. Yeah? So if your company comes, look, this is our problem, solve it. Well, you will be the one analyzing the problem, choosing the right technologies, training the correct models and so on, optimizing the models, deploying the models, and make sure the customer is happy. Yeah, so very hands-on program. Nevertheless, I think we cover the entire spectrum of what is AI. Yeah, so from data science to training the different types of models, to reinforcement learning, to deploying the models, and this way you can implement the entire pipeline. Also interesting, yeah, each semester finishes with a project, a big project, a 5 weeks project where students will work full-time on that project. Yeah, exams are done, yeah, they will work full-time, and that's exactly what we come here for. The idea is for next year is to have our students in Belgium come here for 2 weeks and work together with Vietnamese students, PTIT students, on an industry project. A Belgian or probably Vietnamese company providing projects, and mixed teams of Belgian students and Vietnamese students will work on this project. And then after 2 weeks, normally everybody would fly to Belgium and continue working on the project over there. That's the idea we're having. Yes? So maybe some of you might be involved in this. But nevertheless, if you would find this interesting and you want to come study maybe only 1 semester, no problem, you can do this. Let's say, look, I want to come to study this program maybe from, let's say, September till December, no problem. You can follow, let's say, a cluster of these classes. Okay? If you have more questions about this, or if you find this interesting and so on, you can come ask us after the session here. And also there's some information available here. Okay? Yes? Look, I'll get it out of your way. Yes. Okay. Any questions on this? No? Not yet. Okay. And then, of course, what you're all here for is this session on generative AI. Yes. If I would ask you if I ask you the AI, what does it mean to you? Anyone? What is an AI system? Actually, it's a system that can do things where before you needed human intelligence to do this. Yeah, so it can actually replace human-like tasks. Yes? Okay. Now, AI is basically nothing new. Yeah. Already, for example, in the 40s, people were trying to develop, the 40s of the previous century, people were developing or trying to develop intelligent systems. They did not call it AI yet, but it originates from there. And in the 50s, this guy, Alan Turing, he already came up with the Turing test. And this is quite an interesting concept. His idea was, like, if we ever develop intelligent systems, AI systems, how will we test their intelligence? Anyone familiar with this test? No? So here you have a human, can be you, and you can ask questions, any type of questions, like how do you feel today? What will you do next weekend? What is the weather today? And so on. Any type of questions. Okay? And this question can be sent to the left or to the right. On one side is a human person, on the other side is an AI system. Except this person asking the questions doesn't know who is where. And if after asking a lot of questions, the person still doesn't know which side is the AI system and on which side is the human person, it means the AI system was able to fool that the human questioner. Yes? And that means that the AI system passed the Turing test. And if you would have asked me a couple of years ago, and are there already any AI systems capable of passing the Turing test, I would have said absolutely not. But then came, of course, ChatGPT. Yeah? And as of today, yeah, many of these types of models, they easily pass the Turing test. Yeah? So a lot has changed the past years, of course. Yeah? So where are we now? We are moving in the direction of what we call artificial general intelligence. Yeah? So until recently, AI was capable, sometimes more capable than humans, in doing very specific tasks. For example, detecting a specific type of tumor, could do it perfectly, but don't ask it to do anything else. Yeah? Right now we're moving towards systems capable of doing many different types of tasks across different domains. Yeah? So we're moving in the direction of artificial intelligence, and there is a big discussion if we're already there or not. Yeah? Some say yes, some say no. Okay. Good. If we talk about AI, artificial intelligence, actually that's like a big umbrella, a big container, yeah, of all types of systems, software that is capable of doing things where before we needed human intelligence for. Yes? And the AI that we use today is actually based on what we call machine learning. Is that concept clear? You have heard about this term, machine learning? I think it will be one of your classes next year, maybe. Yes? So machine learning is actually a collection of, again, systems, software that can do tasks, that can do things without them being explicitly programmed to do this. Yeah? So I heard from you have learned to program in, what is it, Python, Java, C++ maybe. Yeah? So what is a computer doing? Actually, sorry? Following your instructions. So it's the programmer telling the computer what to do, right? For specific tasks like computer vision and so on, that doesn't work. As a programmer, it's impossible to determine like how can you program a computer to recognize my face based on all these different pixels. It's impossible. So in machine learning, how do these systems learn? Just by looking at a lot of examples. So we give them a lot of examples. And as an example, let me show you this one. Oh wait, might be here, I guess. Yes. Recognize this? This is what we call a BSF, a black soldier fly. And it's like an animal 1.5 centimeters. Yeah, no. The width of this animal, not that big. And this is an interesting insect in the production of proteins, because the eggs of this fly contain a lot of proteins, and they can use it in the production of animal food. So a very cheap way to produce animal food. Now what is important is that for the female fly to have a lot of eggs, to grow a lot of eggs, is the right ratio between males and females. So if you keep these flies in a big cage, yes, if there are too many males, the females get stressed and very little production of eggs. If the amount of males is too low, not much will happen and the production will be low again. Yeah, so you need the right ratio, about 30% males, 70% females. Yeah. So a Belgian company decided to create a kind of device that you input like 10,000 of flies, like a big container of flies. These flies will be kind of attracted by UV lights at the other end of the machine, and to get to the UV light they have to pass through a tube, glass tube, one by one, but it goes very fast. And while they're passing through this tube, a camera is looking at them, like you see here, and then an AI system will decide whether it's a male or female. And if it's a male, then with air pressure, this fly will be blown into one container, if it's female, into another container. Okay. And surprisingly, the system works very well, like 99.9% accuracy. So if you do 1,000 classifications, on average, only one will be wrong. Yeah? Question, how do you train such a system? So you need an AI, but this AI needs to see a lot of examples. Yeah, so you collect a lot of pictures of these flies, maybe 1,000 male flies, 1,000 female flies. That means that biologists, for example, have to go through this entire data set and label these flies, male, female, and so on. But once you have a labeled data set, you can show it to the model, and the model will start to see patterns and say, look, each time I see this pattern in the image, turns out to be female or male. Yeah? And after some time, that works very well, even to a level that it recognizes these flies much better than humans, than biologists. Because very often we had a detect or a classification of a fly, and the biologist had to say, I don't recognize it. Usually they look here at the tail section. And the AI was correct. If you do dissection or you look at this fly under a microscope, the AI was correct. It could see patterns that people could not see. And what is also interesting about AI systems, they can not only make good predictions, but they can also help you to get insights. Like, why did this AI decide it's a male fly or female fly? And here, these are the interesting areas where the AI was looking at. Indeed, just like biologists look at the tail section, but apparently it also was looking at other sections in the image, parts of the fly. Yeah? And that's always also a very powerful aspect of AI. It can give you insight in your data. It can give you insight in customers, how customers behave, and so on. Yes? Okay, not to lose too much time. Yes. If we then talk about deep learning, it means, again, this is machine learning. We learn from examples, but we use a specific technology called neural networks. And this is a bit inspired by how the brain works. And there we also use kind of artificial neurons, just like the building blocks of our brain. We connect them in a certain way. We train that neural network, and hopefully it can make good predictions. This is the more conventional machine learning is especially good at making predictions and kind of finding patterns in structured data, like Excel-like data. Yes? This one's deep learning. That's the way to go if you have to deal with unstructured data, like images, video, text, sound, and so on. Yeah, but that's all stuff that you will learn in the coming months or years. Yes. And then within deep learning, we have this new field, new, already a couple of years old, actually older, but very popular now the past years. It's this generative AI, where AI models do not only make predictions, they will not only say it's male fly, female fly, it's this face or it's another face and so on. No, they will generate very realistic data themselves. So the output of the model is not only prediction, but it's data. Yes? Very quickly, how do you think conceptually that these systems can learn from examples? Well, AI system, I'm taking shortcuts here, and not all of them, but many of them, they learn in a very similar way as we learn, as humans. So how do you know this is a table here? Because someone told you, right? Yeah, maybe your parents told you this is a table, or be careful, don't hit the table. This is a chair, and so on. Yeah? So if you learn in this way, where you see an example, and each time you see an example, you know the correct label, you know the correct answer, that's what we call supervised learning. Supervised, there's kind of supervising, tell you each time what you are seeing, what you're doing, and so on. Yeah? So you learn from a labeled data set. We can also learn from just observing the world. No one will tell you anything, but you just look at what happens. Yeah? You start to see relations between things, similar things, and so on. This is what we call unsupervised learning. Yes? And then maybe one of the most powerful techniques of learning is reinforcement learning. And actually that means learning by doing. Okay? So you can show a child 1 million times how to drive a bike. It will not manage to drive this bike unless it will try many times by himself, just by falling on the floor, hurting himself and so on. But you have to do it, right? So very often just by doing you will learn something. And this is indeed reinforcement learning. I'm sure all of you are using ChatGPT or some other generative models. Yes? ChatGPT is available here, right? Yes, because sometimes we don't get access to ChatGPT. Sometimes on the Wi-Fi, yes, but on 5G it's not always available. Is that normal, or? It's not what you're experiencing? No, okay, good. If we just talk about ChatGPT, what types of learning would be involved? Well, we'll have a look at it, okay? Yes? Sorry?
Maybe as the three resources learn from.
Yeah, well, mostly it will be like self-supervised learning, yeah, and then also reinforcement learning. Yes? Oh, but I'll come back to this. Okay, so here this I will skip. Maybe I'll just show you this one because it's a funny one. This, and probably you've already seen it. It's like a classical example of reinforcement learning. Yeah? So what you basically have in reinforcement learning, like you typically have an agent, and an agent can be anything making sequential decisions, like a robot walking around, a vacuum cleaner driving around. But it can also be a trading bot, but here some, let's say, characters in a computer game or something. Yes? And here you have two agents, the blue one and the red one, and they will play hide and seek. Yeah, so the blue one needs to hide himself, and the red one needs to find the blue one. Yeah? So the behavior of these agents is completely learned by the agent. So there was no programmer writing the rules of how they should move. These agents initially they have zero idea about the rules of the game. They don't know anything. Zero. Okay? Good. And by playing the game, they will start to learn the rules. And how do they learn the rules? Well, as soon as, for example, here, the red one can spot the blue one, he will get what we call a reward. Like you did very good, like he gets a kind of the score goes up. And the longer the blue one can stay out of sight of the red one, also the score is going up. And what they both try to do, they're in competition with each other. They try to maximize their score. And they try to figure out what is the best way to maximize the score. And that's how they learn the rules of the game. Yeah? It's like you're driving in traffic here. Yeah? What do you try to do? You try to maximize, or actually in this case minimize, the time you will spend to travel from one point to another point. And what is your strategy? Like, yeah. Okay? So, and this is what happens. But this is after hours and hours and hours of training. Yeah, running the simulation on specialized hardware. So what you'll see, here, that even after some time, the blue ones, they have figured out that if they block the entrance, they can hide themselves from the red ones. That's even after days of training. But then the red ones will figure out, if they use this ramp here, they can climb over the walls. Yeah, so here the blue ones are very proud. Look, they're hiding. And the red ones figured out to do this one. And what will be the next step? Yes, they hide these ones. Okay, game over for the red ones. Yes? Okay. Okay. Just very quickly, because we will dive a bit deeper into generative AI. In generative AI, we typically use neural networks, inspired a bit by how the brain works. And a neural network is built with specific building blocks called neurons. And we have billions of them in our brain. And all these neurons are connected with each other. So, and these connections play actually a very important role. Yes? Now here, this is like a schematic of one neuron. And what is this neuron doing? It's something that we do constantly. It's actually, and again I'm taking shortcuts, I'm oversimplifying. But a neuron is making decisions. Yeah? So let's say that tonight someone calls you, a friend calls you and asks you, look, tomorrow it's weekend, will you join me to go visit something, or go drink something, or go to a party, whatever. Yeah? Then in your brain, a lot is going on, and then finally you will produce an output, right? You will give an answer. Well, here, if this neuron will get different inputs, different things that you take into account, like, is it gonna rain tomorrow, yes or no? How much will it cost me? How far away is this event, and so on. And then to each of these inputs, you will assign a weight to it. Like, how important is it to you? Like, if you do not have any money left, I mean, the price of the event will be very important, right? And you probably will assign a negative coefficient to it, because the more expensive it will be, the event, the less likely it will be that you will go there. Yes? Okay. So each of you will have different weights assigned to these inputs, because what is important for one person might be less important for another person, and so on. Yeah? And then you sum up all these weighted inputs, and here the sum, in this case, it's 1.2. It's not very meaningful. That's why usually this sum is converted into another value, another number, and for sure you will see this in machine learning classes and so on. And this can be read as kind of a probability value. So if your friend asks you, will you come with me tomorrow? You will say, yeah, with about 80% certainty. Yeah? So that's basically what one neuron is doing. If we talk about neural networks, a network, it's a connection of all these neurons. So we connect many neurons, and for example, in the newest version of ChatGPT, we actually don't know how many neurons are there, yeah? How many connections, but I think there will be like trillions of connections. Yeah? Okay, so the more connections, the more neurons you use in your neural network, the bigger the capacity, and the more knowledge you can basically store in this neural network. Yeah? So this is a neural network. You input information. Instead of making one decision, you have a sequence of decisions being made. And the idea is that each neuron will try to estimate something, will try to find a specific pattern, give that information to the next layer of neurons. They, on their turn, we'll try to find some deeper information and so on. And as you pass through the network, you get to discover deeper and more complicated patterns in your data. Until at the output, there you can make a prediction. Yeah, so here, for example, you feed the image of a face, and then it will be analyzed layer by layer, and at the output, like you have 4 different classes, the neural network will typically here output a probability distribution, say with this probability, this face belongs to this person, this person, this person, or this person. And typically, we then choose the class with the highest probability. So, let's dive a bit deeper. How much time do I have? 25 minutes? 24? Yeah, okay. Let's dive a bit deeper into generative AI, unless there are some questions. No? Okay. So, generative AI is a very specific field of AI that has become very popular these days. So, ChatGPT is one example, but in general, these are actually neural networks capable of generating realistic data. It can be generating images, can be generating text, music, whatever. Yes? All right. Yeah, maybe I will skip this a little bit. So it's kind of started a bit with what we call autoencoders. And these are kind of neural networks. See, here, different layers of all these neurons. You input, like for example, an image, and this neural network will try to reconstruct that same image. So at the output, you want the output to be very similar to the input. You can say, why do this? Because you can do, if you just want a copy of an image, just do copy paste, right? Don't use a neural network to input an image and then hope that at the output you will have a very similar image. The idea here is that we do compression. So the image is compressed, and from this, you see this bottleneck here? From a higher dimension, a lot of pixels go into a smaller dimension, and from the smaller dimension, you go up to a higher dimension. Yeah? So here the neural network learns to detect the interesting pattern, the essential patterns, allowing the neural network to reconstruct that same image. And you can use it for compression, but what you can also do, and again I'm taking a bit of shortcuts, if you, let's say, have an image of a cat, of a face of a person, yes? And you compress that image, you send it through this neural network, and you can see how the neural networks has compressed that image. So you look at the values here. If you slightly change these values, slightly tune that values, what will happen if you can reconstruct these values? You might still end up with a cat at the output, but a different one than the one that got into the neural network. Okay, so you still have the characteristics of a cat here, the values of a cat, you change them a little bit, and you can make reconstructions. Anyway, a lot of shortcuts, but that's basically the idea. You can use it for denoising. Yeah, so very noisy images, you can clean them with such types of neural networks. Another type of neural network, and for sure that will be also part of the curriculum, that will be, I think, part of your deep learning class or generative AI classes. It's called a GAN, Generative Adversarial Neural Network. And the idea of a GAN originates by a guy, and now I forgot his name, it will come back. He figured this idea, just by drinking some beers with his colleagues. So they were just having a discussion, and then he said, I found some idea. He went home, still a bit under the influence of alcohol, I would say drunk. He started programming, and he invented the GAN. And what is a GAN? A GAN actually consists of two AI systems. And one is called the generator, and the other one is called the discriminator. Yeah. What will happen? Look here, this discriminator, let's say we want to generate realistic face images. Yes? So a discriminator, it's a neural network that is trained to see if an image contains a face or not a face. So if I show it an image of a table, it will say, not a face. If I show it your image or your passport picture, for example, it will say, look, this is a face. So this one is very good at saying what I see is a face or is not a face. Yes? This one here, the generator, this is the one that will try to generate faces. And in the beginning, it has zero knowledge of how a face looks like. See, it has no access to a data set of real-world images. It has no idea how the face looks like. Yes? Yeah. So what it will do initially, if you ask generate an image, it will generate like a random pattern. And it will show it to the discriminator, and the discriminator will say, aha, look, it's very clear this is not a face. Yes? And then there is a bit more complex theory behind it, but actually then the generator will get some knowledge of how the discriminator could see it's not a face. So next time it will generate an image, it will be able to fool the discriminator a bit more by generating an image which looks a bit better like a face. Yes? And each time this one generates something, it shows it to the discriminator. The discriminator say, yeah, face, no face. If it says no face, then for this guy, this one will get some more knowledge. So next time it can generate a better face. And these are some results. Yes? Okay. These GANs were very popular a couple of years ago. They're still used for specific cases, like to optimize faces, to denoise, to upscale, resolution upscaling. You have a low resolution image. Yeah? You can upscale it to high resolution images. Yeah? I think it's even used in Microsoft Teams to save bandwidth. Yeah? So the camera will detect your face. A very low resolution image will send through to the other side of the Teams connection, and there again will kind of upscale that image, so the quality is again quite good. So a good quality image with very low bandwidth. Okay, and then we come to state-of-the-art models and the large language models, just like GPT. So why do we call them large language models? Large, because these are huge neural networks. Yeah, for sure, maybe in some of the lab sessions you will train neural networks locally on your computer. Yeah, like small neural networks, you can run them on any laptop I see here. Yes? Yeah. These large language models are so big, they will not even fit on all laptops here in this room, or maybe here in the institute here. Yes, so they're huge, large. Why language? Because we interact with these models by language, by typing a prompt, by showing an image, by talking to them. Yes? Okay, and even though that each time we use these models we are impressed by what they can do. They can produce like texts of code, they can write poems, they can write software and so on. They can write websites, they can tell us jokes and so on. But in essence, actually, they are just a fancy autocomplete. Just like you have on your phone, if you start typing a message, what happens? You get some suggestions about what might be the next word. Yes? So, if ChatGPT is generating an answer, typically you see this writing process. Yeah? You see this generation going on. Yeah? And what is actually happening is that you type a question and then the model tries to predict a word, the first word of the answer. Yeah? Then that word is fed back into the LLM. Yeah? For example, here, once upon, and the LLM predicts A. Yeah? Then what is then fed back into the LLM, once upon A, and the LLM will try to predict the next word, time. And then that sequence is again fed into the LLM, and this is the output. And that's why this process, you see this process going on. Yeah, so each time a new word is added and the entire sequence is refed into the LLM. Okay, good. So it takes a lot of compute, right? So a very fancy autocomplete. Yeah. Actually, what the LLM is doing, it's not really predicting a specific word. It's actually producing a probability distribution. It's at the output, it will produce like a list of maybe 100,000 of words, and for each word it will tell you, look, this word here has this probability of being ending up as the next word, and this one has a much lower probability, and so on. Yes? So which word is then chosen? Well, the most probable word, next word, is time, right? Yes? Have you maybe heard about that you can set a temperature value for your LLM? Yes, like how creative your LLM can be. If you set your temperature value very low, almost 0, it means that it will almost always pick the one with the highest probability. Yeah, so you will have more consistency in your LLM. It will almost always produce the same answer. If you have a higher temperature value, then you will allow your model to pick values with a lower probability. And then it can become very creative. And each time you ask the same question, it might come up with different answers. Yes, so that's what the temperature value is basically doing. Yeah? How are these models trained? Well, that's very challenging. Not going into too many details. But the first step is to get your hands on a lot of data. So if you can, you download the entire internet. Yeah, so all text you can find, Wikipedia, all emails, forums, Reddit, and so on. All you try to download everything. And then you train that neural network. It's a kind of a transformer neural network, or as a next word predictor. So you give it a piece of text. So from all this down, this entire corpuses of text, you give it a piece of text, and you train that neural network to predict the next word. Yes, it's computationally very expensive. This process takes weeks, months, sometimes on 100,000s of specialized GPUs. So this is not something that you can do on your computer. You need millions and millions of dollars of electricity costs. Microsoft is even opening let's say an old nuclear power plant just to power the AI systems for this specific training process. It's huge. Okay, so that costs a lot of money, a lot of resources. Then this model is very good at predicting the next word. Yes, but that doesn't mean that it can give qualitative answers, that can give good answers. Yeah. And that's where kind of people get involved. See here, supervised fine-tuning. And what you have here, there you use a list of, let's say, 100,000 of questions that have been answered by humans. So you have questions, and humans will write the best possible answer. And then the model that has already been pre-trained will then be trained on this data set. And surprisingly, this way your model will turn kind of all its knowledge that it has seen here into giving good answers. Even it can answer questions that were not in the list, because here it acquired knowledge, it could see relationships between words, it can understand certain concepts, and here in this phase it learned to turn these concepts into answering. Yes? And then there is a third phase, like reinforcement learning with human feedback, where, and maybe you also had it, that sometimes ChatGPT will give you an answer. Yeah? But sometimes it will give you two answers, two different answers, or three different answers, and you will have to pick the best one. Yeah? Well, actually, if you pick the best one, you are helping the model to become better. It will learn from your feedback. You say, I found this answer to be the most accurate one, the best one. Yeah? And with this feedback, reinforcement learning models will make sure that the model can improve itself. Okay, now, and this is already a bit of an introduction to what Dieter will show you in about 20 minutes, maybe. If you write a question in ChatGPT, whatever, yeah, you write. Yeah. Actually, here, this piece of text, what we do, we will convert your text into what we call tokens. Token. And a token can be, you can see it as a word, but very often it's also a piece of words. For example, here this word indivisible is split into two tokens. Yes, so a token, you can see it as a word, but very often a piece of word. That has the advantage, if a word is misspelled, is not written correctly, then it's only a piece of that word. It's only one token that contains errors, but the other token is still correct. Yeah, so it has certain advantages, but also some disadvantages. For example, here, these numbers here, this is like one token. 1, 2, 3 is seen as one token. Okay, so anyway, so that's the first step. So convert this text into individual tokens. Now, you can imagine that such a neural network, yeah, it's like making computations, right? And to make computations, what do you need? To compute something, you need numbers, correct? Yes, so just making computations on words, you will not be able to compute much. So these tokens will have to be converted into, hopefully, meaningful numbers. Yes? And like the first step, and this is something that they were doing years ago, is you have a huge vocabulary, like all possible words in the world, let's say, yeah, or in English or in Vietnamese. I don't know how many words are there in Vietnamese. 150,000, 200,000, I don't know. Yes? Okay. Or in English, maybe 200,000. What you then do is, for each word, for each token, you will check the position in that vocabulary. And so you have your list of all possible words. You try to find it. Look here, the word many, where can I find it in my vocabulary? And apparently it's on position 12,488. Yeah? So the word many gets converted into this number. And this, the word words, gets converted into this number, because this word here is at position 6,000 and so much in the vocabulary. Yeah? Like here, typically the word black would get number 2,409 and so on. what is the problem with this? Actually, it's very simple, right? Yeah, you want to convert a word into a number. You check the word, you say, look, where can I find this word in this vocabulary? At position so much, and that's exactly the number I give it. But you agree with me that there is no meaning behind that value? This number only tells you where in the vocabulary you can find that word, but there's no kind of semantic meaning to that number. Yeah? Okay, and that's why each of these words will be converted into a vector, into a list of words. So instead of like one number, we will convert it into a kind of vector of different numbers. And this vector of numbers, like I will show it in a minute, this is what we call an embedding. It's a very important concept, embedding. Yeah. And here, I'm not sure if it's really visible. Here I have a couple of words like cat, kitten, dog, houses, man, woman, and so on. Yes? And instead of assigning, again, one value to each of these words, we assign a vector of values. And so this word is now represented by these, well, how many? 2, 4, 6, 7 values. Okay? Good. In practice, like in GPT and so on, typically each word is represented by a vector of dimension, I don't know, more than 2,000 values. Yeah? Okay, so to encode one word, you need many values. And what is the advantage of this? Well, words having very similar values. So where the Euclidean, you know the Euclidean distance, right? The distance between points in a space. If the distance is quite small, yes, that means that these words have kind of similar meaning. Yes, understand? Like maybe cat and dog, even though these are different animals, they might have very similar values because both of them are animals, maybe pets, and it's very similar characteristics. Okay, good? So that's one thing. If we would be able to see each word, it has a vector, you can see it as a point in space, a multidimensional space, right? Even if it's like a 2,000 dimensional space, each word is a point in space. In so many dimensions. Well, if we would look at a direction within that space, then we could say that a direction in that multidimensional space gives meaning to that word. Yeah? It corresponds to a certain meaning. Look, if we go from here, the word Vietnam to Hanoi, yes? What does this arrow actually mean?
They are relevant.
Yes, but look, here we are in a three-dimensional space, right? Yes, meaning that each word here would be represented by three values. A value on the x, y, and z axis. Correct? Yes. If we go from this point to this point, we travel along this line here. And we go from Vietnam to Hanoi. Yeah. Well, if we start from Japan and we travel in the same direction, we end up in Tokyo. So that direction actually has the meaning of capital. What is the capital of this country? Yes? So if you work with systems, let's say with thousands of dimensions, each direction in that space gets a meaning. So that's where ChatGPT gets its meaning from. From all these values and the relationship between these values, it can see, here he's talking about the capital, he's talking about this, and this. Okay, good. So that's why these embeddings are so meaningful, so important. Yeah. Okay. Let's say here I have. Dieter, do I have 10 minutes? That's all I need, basically. Let's say I have a couple of words, yeah, like bird and cat and dog and so on. And the embedding vector is very small, only 2 dimensions. So I can plot it here in 2D. Yes? Yeah. So this bird has a first value this big and a second value this big. Okay, good. And all the other things. Now, if I would have to position the word ball, what vector would be assigned to this? Probably here, right? Yeah, because this ball is much more similar, has more affinity with these other sports equipment. Yes? Okay. So probably this ball, if we would do this embedding, and Dieter will show you how these embeddings are done, this ball would get also an embedding vector, like 2 values. You know, in practice it's thousands of values, yeah? But here, for the sake of simplicity, 2 values, and we'll end up somewhere here, right? Yeah. Similarly, if I would have the word penguin, probably it will end up there somewhere. Yes? But what if we talk about the word bat? Ouch. Because this can have different meanings. Yes? The word bat can be used, a bat in baseball. Yes? But can also be the animal. And the older systems were just assigning an embedding, yeah, somewhere a mix, somewhere in between. Because in some texts we were talking about sport and sports context. Sometimes it was in the context of animals, and the embedding for the word bat ended up, okay, not fully correct, but somewhere in between. And then if the neural network was seeing this word bat, yeah, it didn't really know much if it's talking about sports or about, let's say, animals. Yeah. And then came the transformers, like this new type of neural networks used by, for example, this ChatGPT. And what is the idea? Well, the word bat, yeah, before it got its fixed embedding. What we will do now in transformers, the neural network itself, like GPT or something, they can change the embedding values based on what we call this context words here. So you look at other words in the phrase, so you try to get some context, some more meaning from the other words, so that you can adjust the embedding of that word in the direction maybe of sports or in the direction here of animals. Yeah. For example, here the bat spread its wings wide. So clearly we're talking about the animal, right? Based on which words? Probably the most important word here is wings. Yeah, it's a very important word to know what we're talking about here, to give meaning to that word. Yeah? And what we're actually saying is that this word here, wings, attends to the word bat. And then we will talk about attention in these networks. Yes? So, actually, we start here from the word bat here, somewhere in between. And because we look at the word wings and maybe spread and its and wide and so on, yeah, to know how we should adjust that vector, so in which direction we should bring it. And it's like these important words, wings and spread. Yeah? These ones are pulling the vector bed in the correct direction. Yes? Okay. And without, I don't have time to go into details, but this is what you will see as attention in networks. Yes? So the vector bed will ask a question, who can give me more information? I want to know who I am. Yeah? And then all the other words in the phrase will respond. I can tell you this, I can tell you this, I can tell you this. Yeah? And then the word bed will be adjusted. So the vector will be adjusted to give it the correct meaning. There's a question?
Yeah, sorry, but so I'm just saying that they are becoming the movable vectors, so that in the structures as you mentioned, so every vector will be a movable
yes,
vector.
actually
right?
every vector will move.
Oh, so
yes.
does it become a bit of misunderstanding?
Yeah, but actually all vectors can move, but the ones that got attended to the most will move the most, of course.
Oh, so,
okay.
So that becomes that the models will be easier to be misunderstanding, right?
Yeah, but it's like one huge matrix multiplication. Like every word will ask who can give me an update about what I should do. And then all the words will respond. I can tell you this, I can tell you this. And then you take let's say the in product, or the how do you say, the matrix, the product, the in product, yeah, of these two, the dot product, sorry, of these two matrices, and from this you can compute how much each vector, how much each word should be updated. That's the attention mechanism, but I'm sure you will learn more about this later on. Yeah, but very good question, yes. Okay, so that's actually here, all the matrix multiplications, but we will not go into details. Yeah. Okay, I think this is for something later. Some tools, I'm sure, look, you know that recently GPT-5 was being released. That's the model you typically use, or you use like Gemini and so on, or Claude, or
computing, those kind of things, DevOps, MLOps. I'm more a practical guy. And today I'm going to show you some demos on how you can use the stuff we've seen with Wouter, the embedding technology, how you can use that in real life applications. So the technique of embedding is used more and more, and it's used a lot in search. And today we're going to use vector search as an example on how you can use embeddings. Wouter talked about text, convert text into a vector representation, but you can also use images. You can create an image, or you can create a vector from an image, or you can use even sound, and so on. So it's more than text alone. The demo I will show you today is text. I have a demo with an image, but there's an issue with the Hugging Face API right now, and it doesn't work, but I will show you the code, and actually it's not that difficult. But embeddings is only part one. You've seen how it works, how you can, or what an embedding is. I will show you how you can create those embeddings using APIs, using code. But the next thing is we need to store them. And to store data, you need a database. I think everyone knows SQL databases like MySQL or SQL Server. Well, embeddings can be stored in such a database, but there are also specific or specialized vector stores. So there are companies building database specific or specially for those type of data. And the last thing we need is we need kind of search technology to search for a topic and search that data into a database. So we're going to show you, or I'm going to show you, small examples on how you can use embeddings search vector databases. Now, before we go to vector search, what is keyword search? And that's the thing we are using for now more than 20 years. Google is a keyword search. You enter a search, you enter a question, you enter some words, and then that engine spins off and looks for answers. If you know SharePoint, it works the same. And you have a question about a document, and you enter your question and it searches. Now, how does it work? Well, it looks for the correct words. I know there are special search algorithms, but to keep it simple, let's say a normal search engine will look for the words in your question, and it will look in the database to find records that contain those exact words. It doesn't know the concept of context. A normal search engine, or an easy way of searching for data. So the pros are, it's very simple and easy to use. We know it for years. It works. It's fast. It's efficient. It can scale to very large data sets. Google is the proof. We have a lot of search engines and tools that use that keyword search. It's very cost effective because we know how it scales, how we can scale it, how we can optimize it. And it's easy to implement. Okay, so that are the pros of keyword search, the stuff we're already using for 20 years. The cons are, it can be inaccurate. So I think everyone has been in a situation where you have to Google for something and it takes some time to find the correct answer because it doesn't really understand the meaning of your question. Of course, typos, these days that's not a real problem anymore, but in the beginning days of search, if you made a typo, you could get completely wrong answers. But that's already fixed now. But the most important thing is it does not understand the semantic relationship between words. And remember the slide from Wouter 10 minutes ago about how embeddings understand relationships between words. That's one of the advantages, that's one of the things that embeddings fixes. And of course there's a language barrier. Search engines need to be optimized for specific languages. Now, what is vector search? Well, here vector search will understand the context of the problem. So the system understands the intent behind the question. You have a problem with your laptop and you want troubleshooting steps to fix that specific problem, and the problem is the laptop doesn't boot. It knows that if the laptop won't start, well, it's the same as it doesn't boot. So now it understands the context of your problem and it can retrieve documents that don't use those exact words. So things like troubleshooting guide for computers that fail to power on, that describes exactly the problem we have. It's the same context, but the words are different. With a normal search technology, that would be quite difficult to find that document. With vector search, you will get that document in your results. So, another example of missing context. If you enter Java, I think it's one of the programming languages you are learning, Java. It's also an island. So if you search for Java, what must the search engine choose? There's also a coffee brand. So context, very, very important word. So, kind of a definition, and vector search is a method for finding and retrieving data based on semantic meaning, rather than the exact keyword matches. And it also leverages machine learning models to represent text. So if a machine learning model, an LLM, whatever, works with pictures, text, it will always convert that to an embedding. So, The pros, well, better understanding of the semantics. Already talked about that. You can handle, or it can handle complex and ambiguous queries. It's not really a problem for typos. It's smart enough to figure out the correct words. Yeah, back. And of course, it can be used for cross-lingual search. So language barrier is gone. The cons, well, it's expensive. Actually, it's very expensive. That's one of the main problems right now. Wouter talked already about that. And I will show you how you can create embeddings in the cloud, but also locally. But it's an expensive technology. So you need a lot of raw computing power if you have a lot of documents to process. And if you don't have that computing power, you need to go to the cloud, which is also expensive. I don't know which kind of, or do you see any cloud platform here in your in the courses? Is it AWS, Azure, Alibaba Cloud? I don't know. Sorry? Alibaba Cloud? Yeah, AWS? Azure? Sorry? Okay. So, you can, I will show you later on how to run models in the cloud, but in the end it costs you a lot of money. So that's one of the cons. Second thing is it's also harder to implement and to maintain. Why? Well, you need to create an embedding of your document. Let's say you have a PDF, which is a much used example is converting PDFs into vectors. Let's say you have 10,000 of manuals. You convert them to an embedding. You build a search engine that can search in those embeddings. But PDFs are updated, manuals are updated. So you have to have a software system that maintains versions. Every time there's a new version of your PDF, you need to recreate the embedding, store it again in the database. So it's much harder to maintain embeddings, specifically if the source data changes a lot. So that's one of the cons. Requires a large data set of pre-trained embeddings. Yeah, but I'm not going to discuss that now. And not as well supported by existing search engines and other tools. That was true, but now more and more products like, I'm an Azure guy, so I use a lot of Azure. You have Azure Search, which is a built-in search engine into Azure. It's just, you can activate it. There's a free tier. It works very well, and it now includes embedding support. So if you building a software product, you need some kind of search functionality. I would really recommend to look into Azure Search. It's out-of-the-box search engine. And it has now support for things like embeddings. So tools are coming, products are extended with embedding support. All right, so how does this all work? Actually, this is kind of the process. First of all, you need data. An image, document, audio. The demos that I will show will be data. We have to convert them to a vector representation. Remember what Wouter showed you. To do that, we need a model, an embedding model. Yeah? Once we have that vector representation, we have to store that in a database. And then we have one of the algorithms that will compare the search query with what's inside our database, and it will show us the results. So we have some kind of interface, can be a web page, can be a console application, doesn't matter. We are entering a query, That query needs to be converted to a vector representation, and then it will be sent to the database, and one of the algorithms, like the nearest neighbor algorithm, will compare my search query, which was converted to a vector. It will be compared to the vectors in the database, and it will show me some results. Of course, it's important, if you're using an embedding model, a specific embedding model over here, you have to use the same embedding model to convert your query. It needs to be the same. That's important. Okay, so in general, what do we need? We need data, a vector database, embedding model, and of course a client application. Let's have a look at the vector databases. So what is a vector database? Well, we all know, I think everyone knows what a normal relational database is. Yeah, MySQL. Do you know NoSQL databases? Are you familiar with that concept? Sorry?
Like MongoDB?
Yes, MongoDB. MongoDB is yeah, it's a NoSQL database, indeed. And now we have vector databases. Any other databases? Sorry? Yeah, indeed. ChromaDB is vector database. Postgres with an extension, correct. And there's one last database, just a small check. Time series databases. Do you know the concept of time series databases? Ever heard about that? What? Postgres? No. No. InfluxDB. InfluxDB is a time series database. It's a database that's used a lot in IoT because it's, well, it's not completely true, but most of the time you only write data with a timestamp. Let's say a sensor writes certain value at a certain time. That's a time series database. It's not important for now, but those are four kind of databases: relational, NoSQL databases, or non-relational, vector database, time series. So we will use a vector database. Yeah. So it's specialized type of database designed, highly optimized to store those vectors. And like you said, you have special databases that can only store vectors, that are highly optimized to store those vectors, but there are also extensions for existing databases like Postgres, and I think SQL Server now also has support to store also embeddings in their tables. It's a kind of a data type that you can create in a column to store vectors, because, well, of course you cannot rewrite let's say you have a specific application and you want to start using embeddings. Of course you cannot rewrite the whole application and do everything in a vector database. You have chosen, let's say 5 years ago, for a specific database. It would be great if you can add some vectors to your existing database. So it's not always necessary to use a really full-blown vector database, but if you are building new apps, new applications, it's something that you can have a look at vector databases. What I've also seen is that some people are using, for a specific app, they're using two databases. They have one for the relational data, and then they have one specific for storing the embeddings of the data. So it is possible to mix them. That's not a problem, you can do that. So that database is highly optimized to store the vectors, but also to look up, to search for vectors that are stored in that database. So actually that's what we call the similarity search. It will look for the closest vector to the query that was sent to the database. So, vector database, I think I already told you the most, stores the vectors, high dimensional, vector of an image or a text or something else, everything is possible. It uses similarity search, and there are some algorithms like ANN and nearest neighbor. Then those are the things that you can choose in your database when you are creating the tables. And that's also important, of course, it has to scale. And these days, everything has to scale. I think if someone here wants to build an application, I think the dream is that millions of people will use it. So that also means that if you have that dream, you have to think about scalability. Yeah, and always think about scalability from day one. It will save you some trouble. Okay, so where is this used? Well, RAG, retrieval augmented generation. Does anyone know what this is? Yeah, okay, I will show a demo at the end. Recommender systems, text semantic search, similarity search for images, videos, audio, molecular similarity research, and so on. So it's already used a lot in a broad range of areas. Okay, what is the current landscape of vector databases? So what can you use? Well, we have closed source and open source, like always. On the right, on the left side, on top, we have the open source dedicated vector databases, which means those are databases that are highly optimized to store those vectors, to store those embeddings. And most of them are brand new, which means they are only a couple of years old. Some companies, some people started developing them. And things like Chroma, Milvus, and so on, Quadrant. Then we have closed source commercials like Pinecoin and Viễn. And then on the right side, we have non-dedicated databases, but databases that already exist, SQL, non-SQL, but have support for vector search. Things like PostgreSQL is a very important one, but also Elasticsearch, Redis Cache can be, or Redis can be used as a database to store embeddings. Cassandra, it's not a complete slide, and because the database that we are going to use is not on this slide. How does this look inside a database? Well, very simple. This is a screenshot from Cosmos DB. I will talk about that later. And here you can see we store the raw data. So the demo that I'm going to show, or the data for the demo, is hotel data, hotel reviews, and we will create embeddings from that review, and then we will search for, let's say, where is the food okay, where can I park, what is a good, which hotel has good beds, and so on. So all those information is in text, and this is an example of an embedding. And we store that data together. Yeah? Is that required? No, absolutely not. You can separate the raw data from the embedding. But in the end, you need the raw data because you have to show the results. You cannot show this to your user. Some vectors, some numbers. That's not a good user experience. So when you're creating embeddings from your text, you have to store your text in a database and the embedding. You can store them together, or you can use two databases. Let's say this in a SQL server and this in a Pinecoin database. Okay. Cosmos DB. Who knows Cosmos DB? No one? Okay. Well, everyone who uses ChatGPT. Everyone, I think. Yeah. Well, that's the database behind ChatGPT. Cosmos DB is a Microsoft Azure service. It runs on Azure. I don't know how many people know that, but ChatGPT runs on Azure, completely on Azure. So it's ChatGPT and OpenAI is not from Microsoft, but they are a deeply corporation. I don't know, I think they have 49% of the company, I'm not sure. But OpenAI, ChatGPT is heavily built on Azure. And the database they use for ChatGPT, so every time you ask a question, it answers, it's stored in Cosmos DB. And that's the database that we're going to use. And you can use that database also. It's a highly scalable, managed database on Azure. What does it mean? It's managed. It means you don't have to install it. You don't have to maintain it. You don't have to patch it. It's very easy to create an account. I think students can have a free account. You pay for what you use. If you only, I don't know, stores a couple of megabytes of data, it will be, I think it will be free. I don't know exact the pricing, but it's a very, very powerful database. They also use it for their own services like Xbox. If you know, I think everyone knows Xbox and the hardcore gamers. Xbox Live, Office 365, all those services use Cosmos DB in the background. So it's not a toy, it's a real powerful database. Also interesting, it's multi-model. What is multi-model? Multi-model means that you can use other APIs. Let's say the MongoDB, you have a MongoDB application and you want to convert it to Cosmos DB. Well, it's very simple. You don't have to change your application code. You just have to import your data from Mongo to Cosmos DB and then change the connection string and it works. So it's multi-model, multi-API. It's a document database, but you can also use it as a key value database, a column database, or a graph database. Yeah. It's globally distributed. It means it's around the world in all the data centers from Microsoft. I don't know how much. I think there are more than hundreds now. So it's globally distributed. It has an unlimited scalability. Yeah. You will not fill it up with data so that it crashes. They have, I don't know, millions of servers. Low latency, a good SLA, service level agreement is very good. Of course, you have some options, and the more you pay, the more service you get. And like I said, it's used by ChatGPT, so everyone is using it in the background. Okay. Some small concepts before I will dive into the code. Well, I'm not going to show you all the codes, that will be too boring, but we'll run the demos and explain the most important parts. But Cosmos DB, how does it work? Well, if you know MongoDB, the concepts are the same, almost the same. In MongoDB, you have collections. In Azure Cosmos DB, you have containers. Concept is almost the same. Inside a container, you can store documents. What is a document? A document is a JSON file. That's it. Very simple. You have, of course, indexing, automatic indexing, a partition key, also important concept. I'm not going to dive into that, but if you are interested in Cosmos DB and you want to play around with it, a partition key, choosing the correct partition key is a very important thing you have to do. It has something to do with how Cosmos DB is organizing the data internally. Then scaling, already told you, it's multi-regional. It scales based on storage, on throughput. It will automatically create new nodes if it feels the need, because one node is too heavily attacked by users and so everyone is reading and writing to a certain node, it will automatically scale out. Okay, so that's Cosmos DB, that's the database. And the cool thing is about Cosmos DB, they extended it with vector database capabilities. So it's, I don't know how old it is, I think maybe 10 years now, Cosmos DB, but it's only public for a couple of years. And they created extensions like you have for Postgres to store vectors. It's very easy to do, I will show you later on. So when you create a container, you can say during the creation process. Okay, one of the properties of my JSON document will be an embedding. Yeah? And that embedding will be, let's say here we have 1536 dimensions. So you have to specify the number of dimensions. Where do you get that number? Who defines the number of dimensions in your database? Any idea? Who creates the embedding? The model, yeah? You have a model that creates embeddings for you. So you have to look at the documentation that you fill in the correct number here. Because you cannot use an embedding model that creates a vector with 500 dimensions, and in the database you want to store it like 1500. So that is one of the things you need to look up. So you have to define how big the vector is, the size. You also have to define the distance functions you want to use. Is it the cosine, the dot product of the Euclidean, and a data type. And that's it. From that moment on, your database container is ready to store embeddings. We also need a policy, a vector indexing policy. I'm not going to dive very deeply into that. It's more advanced, but let's say, depending on the amount of data you have to choose a certain indexing policy. We have flat, quantized flat, and disk ANN. Disk ANN is the biggest, is for very powerful and large data sets. Here we have faster search, but here it scales better. So you have to choose before you get started which one is the most important type you need. Okay, so we are going to use Cosmos DB. I will see in the code which one I've chosen. But now we're ready to start, and we know which databases there are. We know that we're going to use Cosmos DB. Okay, next step, create embeddings. This is a simplified screenshot. We have the data, we send this to an embedding model, and what comes out is a vector. Okay, which embedding model? Well, there are a lot of them. Yeah? You can see here, I think every big company, Google, Facebook, OpenAI, and so on, they all have embedding models. So it's up to you to look into the docs and find out which one is good for me. The quality is important, and I think there are leading boards that you can see online which one is good for what. Pricing can be important, specifically if it runs in the cloud. But then you can start, you choose one of the embedding models. Okay, now we are going to run an embedding model in the cloud. Why? Well, I want high quality embeddings. I'm going to use, I think it's text A.2, which is one of the most used embedding models. It's from OpenAI. But I'm going to run that in the cloud. So how can I do that? Well, of course, you could use OpenAI. I think everyone knows they have a platform, an API that you can use. Of course, you have to pay for it, and it's not free. But I'm going to use Azure AI Foundry. Like I said, I'm an Azure guy. I try to do almost everything on Azure. So I'm going to use Azure AI Foundry. What is Azure AI Foundry? Well, it's a platform in Azure that allows you to discover, manage, integrate AI models in your application. Let's say you're building an application, you want GTP 5 to integrate in your application. Well, you can deploy GTP 5 on Azure AI Foundry, you get an API, and you can start using it. Of course, it will be expensive. Yeah? But there's more than GTP. You have also other models like DALL-E, Whisper, and so on. Let me show you very fast how it looks. So here I am in Azure. I have my Azure AI Foundry already set up because it can take some time. Is my Wi-Fi on? Yeah, it's good. Okay, go to the Azure AI Foundry. So, if you need a model on Azure, the way to go is Azure AI Foundry. If it's for embeddings, if it's for building chat applications, it has a lot of options. It's a very complex thing. You can even build complete chatbots with it without writing any code. So let me show you the model catalog. So these are all the models that you can use. So let's say you want to use, I don't know, DeepSeek. Okay, you want DeepSeek. You choose DeepSeek. Use this model. It will ask you some questions, and it will be deployed. Here you can see the price. It's $2 for 1 million tokens. So, if you're using models in the cloud, you're not paying by, well, the currency is tokens. Yeah? See tokens? So $2 for 2 million tokens. So that's how they bill you. From now on, I could use, and by using this key, I can use, I'm going to hide it of course, but by using this key, you can start using that model. It's as easy as that. It even gives you code in Python. This is the Python code you need to paste in your application, install some dependencies, and you have a basic example. So it's very, very easy to start using models running in the cloud, running on Azure AI Foundry. It's very powerful. If you don't want to use Python, you can use JavaScript. Even it has native REST APIs, you can use Java and C#. So that's Azure AI Foundry. The cool thing is, you can deploy your model, but you're only paying for the number of tokens, which means if you're not using your application a lot, the model is online, but you're not paying any money for it. It's just when you send a request, it has to generate tokens, get a response. That's what you're paying for. You can talk about Azure AI Foundry for 2 hours. It's a very powerful product. Here you can see I deployed DeepSeek, but I also deployed GTP4 Mini, that's for later for the rack, and I deployed text embedding ADA 002. That's the embedding model that we are going to use. So it's also running on Azure AI Foundry. Okay, so we have a database, we have our model deployed to create the embeddings. So what's the next step? What if you don't want to run your application in the cloud? What if you don't want to run your model in the cloud? Are there situations where you do not want to use an embedding model or another model running in a cloud environment? When? Privacy. You're sending your data to a cloud provider. Yeah? Where we live in Europe, they're very, very sensitive about privacy. So all the data has to stay in the European Union. We cannot send medical data to the United States. Not even if it's only for a couple of seconds to send to a model and to send a response. That's not allowed. So all those models need to run in a European data center. But even then, there are companies that are saying, okay, I don't want to run those models in the cloud because it's too sensitive, my data. Well, then you have an option is run your model locally. The problem is you need a very powerful hardware. And installing models can be hard. Most of the time a model is some Python code, you have to run it, install some dependencies and so on. Luckily for us, there are some open source projects like Olama, I don't know if you know Olama, but it's a very nice project. It allows you to run some models local on your machine. And the hardware that you need is not, of course, how more memory you have, the better, but I'm running this on a MacBook Air, which is not that powerful, with 16 gigs of RAM, and it can run some basic models. Yeah? So you have to install it, and then you can, it's very easy, it also works on Windows, and then you can choose a model here, and it will download the model, like DeepSeek, on your computer, and then you can start talking from your application to that specific model and do some stuff. Of course, if you are, the bigger the model, the slower it will be. So the things that I will show you will go pretty fast because it's the embedding model is not that big. But if you're running things like DeepSeek with 7 billion parameters, you need some decent hardware, of course. But it's an interesting case. It's interesting technology if you don't have the money for going to the cloud, or you want everything local on your machine or on a server inside the research lab or whatever. So then you can use Olama. Here you can see. Another product is LM Studio, which is also free, and now you have also Azure AI Foundry that can be run local on your machine. So there are different options. Okay, time for some code. We have the first demo. Now, I'm going to use C# because I'm a .NET developer. I also do Python. I think it's time to create a Python version of this demos. But I don't think it will be any problem because you know Java and C#, they look a lot like each other. Actually, C# was based on Java. And Java was first. Microsoft was jealous. They wanted their own language in 2000, long before your time. So they created their own Java called C#. Okay, so let's go to the first application. What I'm going to do, just a minute. Yeah, it's hard to type and to hold a mic. This will work, I think. Right? Well, it's okay, it will work. It's okay, Wouter, thank you. So let me go to the correct prompt here. So what do we have? Well, we have, first of all, we have data. Yeah? So the raw data is a CSV file with hotel reviews. A lot of hotel reviews. Okay? So we have to convert this to JSON. Transform this. I already did this. And then I get this kind of JSON document. So every record in my CSV file is a review. So there are, I think, 999 reviews. This is already prepared because it takes some time. Now I have to embed every document and convert it to a vector. So now comes the code. Where is my program? Let's see. Yes. Okay. So what I'm going to do, I'm going to, I have a database called vector search demo temp, and I have a container name. Now the hard work happens here in getting the embedding back from OpenAI. So I am going to send every document to Azure AI Foundry to the text embedding model, and it will return a vector. So let me check. This is the code. So this happens here. This 3 lines of code, I am talking to Azure using my API key. This is the name of the model that I want to use in the cloud. I am sending text to that, and I get a vector back. So with these 3 lines of code, send it to a data center somewhere, I don't know where it is, and I get my vector back. And that's it. So it's very easy to do. The most work is setting up the model in Azure AI Foundry. Yeah? And then I have to store this inside a database I'm not going to show all the code because it's just C# code, but how does it look inside my database? Let me go back to Cosmos DB. Okay, so this is the interface of Cosmos DB. Yes. And which one was it here? This one. So I have items, and I already did it, of course, because it takes some time. But this is how it's stored. So this is a hotel in Boston, USA. It has some review texts, a title. Those texts, before I sent this to the embedding model, I am concatenating this into one. So this is becoming one string. Let me show this. It's not here. Where is it? Yeah. Voila, here it happens. So here I am concatenating a review title. I am connecting a large string, and that string is sent to OpenAI, and I get the vector back, and then we store this in our database over here. So now if I run this query, alright, okay, just a moment. It wasn't set up, otherwise it would recreate all those documents. Okay, now I can enter a search query. What happens now? What is the best hotel in Las Vegas with good food? I paste this over here. Enter. What happens now? This is sent to OpenAI on Azure AI Foundry. It will create a vector for this. This vector is sent to our Cosmos DB, and these are the results I get back with the best result on top. And you can see it gets a similarity score. So the database thinks that for your search query, what is the best hotel in Las Vegas? This is the best hotel. And City Las Vegas is the Fremont Hotel. Why? Well, you get the review and the title for the review. And the score, similarity score that was calculated during search is 0.8255, the other one is 0.824, and so on. Okay, so this is converted to a vector, and then the distance function, and let me check which one it is for here, settings, index policy. Here we're using containerized flat. Okay, so that's the first demo. It's basic search. It's not that complex. Most of the code here is to set up the database, to delete the database, and so on, to read the files. And the real work, just calling the embedding model, is 2 lines of code. Okay, next small demo is local embedding. Here I am going to use my local model, Olama, and this will go pretty fast. So this is this one. No, it's this one. So the concept is almost the same, but here I am telling, okay, use the MXBay embed large model. This is a model that is available here in Olama on my computer. And let me run this, and you will see it goes very fast. And here it's not calling Azure AI Foundry, no, it's calling the Olama model locally on my computer. So here I am running that embedding model locally. Of course, it's not as good as the model that is running in the cloud, because my hardware is not powerful enough. So you have to choose for a model that can run on your computer, and one of the most important things here is memory. But you can see here I am embedding about 1,000 documents pretty fast. Okay. In the end, if I go to the database, it will be the same. Nothing special. It's just an embedding with text. Of course, if you would compare the vectors from using text A.2 on Azure AI Foundry and compare them with the embeddings that were generated locally, they will be different. And that's why you cannot mix models. If you embed a document with a certain model, you have to embed the query with the same model, otherwise you will be in trouble. Voila, and now it's uploading it, and then you can start searching. Again, if you are entering a search query, of course the search query needs to be embedded also. Okay. Here I have a hotel with good food. It's the same query, I think, but the results are not as good as with the model that was running in the cloud, because the quality of the embeddings are probably not as good, but I could run them on my own computer. Okay, 2 more small demos and then we're at the end. The first one is image search. Let me go back to the slides. Okay, this is some technical stuff. Like Wouter said, we will provide the slides to, I think, someone. We will find someone who can give you the slides if you're interested in them. This is technical, what you should do if you want to use Cosmos DB and you want to use .NET libraries. What is NuGet? It's the same as pip. And you know pip in Python, NuGet is the system in .NET, so nothing special. This is again explained what's happening, and we're creating a text, we're sending to the embedding model, we get a vector, and then we store this in the database. This is the query that we are using. Local embeddings is the same. Image embedding. What happens with image embedding? This is actually, I think this is a cool one. But you cannot run it locally because you need pretty powerful hardware, and I didn't find a model that can create image embeddings locally. So you have to go through the cloud. I was using Hugging Face, but I think I'm over my API limits, so I cannot show you. But in essence, it's the same. You have an image, you send it to an embedding model, you get a vector back. I can show you the vector. This is here. So this is an image, and this is how it's represented by a vector. So this describes an apple or a banana and so on. And the cool thing is then, if you create a new picture, you create an embedding of it, and the database will look for similar bananas, similar apples, and so on. Yeah? So the concepts are the same. The only difference is you need a special embedding model for images, for sound, and so on. And they are pretty powerful. They are pretty heavy. So you need a good machine, or you need a lot of cloud power to run them. Okay. The last part is RAG, Retrieval Augmented Generation. What is the problem we have with those models? Well, they have a cutoff date. I don't know the cutoff date for GTP5. October 2024?
I think I just it was in my slides. Was it April 25?
April 25. The cutoff date is the date that it's not stop training, but the data they provide to the model was all data before April 2025. That means everything that happens after that date is not known by the model.
April 24.
Claude, yeah, Claude's April 24. You know Claude, the model Claude? Yeah, okay. So RAG is a technique that allows you to extend your model with extra information. Yeah. So, and it's used a lot in combination with vector search. So what are we going to do? We are going to search for something, for a hotel, and then we will provide that answer to an LLM, and that LLM, together with a prompt, of course, and it will get or create a response for us back. That's what RAG is, Retrieval Augmented Generation. So, How does it work? Well, you need an extra model in Azure AI Foundry. You need a chat completion model. Here I am using GPT-4.1 mini. Of course, you can use GTP5 if you want, but one of the things when choosing the correct model is, do you really need those expensive models? If you're building an app, you want to access GTP, do you really need the latest model? Is it really necessary? Because they're the most expensive. Sometimes you can save a lot of money by using GTP4 or GTP4.1 mini, and you will get the same quality of results. That's something that you have to play around with when you're building your AI solution. Okay, so I have deployed GTP4 mini. So what I'm going to do, I will use the same data, the hotel data. I will enter a query, but now the result will be sent to GTP4, the mini version, with a prompt, and it will respond. Let's check this out. It's this one, I think, yeah. So .NET run. Let me paste a search term. Okay, we'll take this one again. Which the best hotel for food? So what happens now? The query is embedded. We create a vector. It will come back. There it is. Voila, we have our similarity score, but the result is then sent to, so this result here is sent to GTP4 mini with a prompt, and you get a better, nice looking result. And based on the available review, the Westin Las Vegas Hotel and Spa is highly recommended, and so on. So, how do you call the chat completion API? It's very simple. Here we are just talking to Azure. We are using a GTP4.1 model. Here we are defining a system prompt. And together with the prompt, we send our result from our database, and the system will answer. It's a kind of a ChatGPT, but with code. Are there any people who already played around with chat completions? No? It's a cool technology. It's like ChatGPT, built in your own application. So you can chat with, or you can build in chat support in your own software. This is .NET, it works on Python, it works on JavaScript, it works everywhere. So that is a very last demo of RAG. This is a scheme, again, how does it work? Ask a question, the embedding, and so on. All right, so this is the last slide. Some info on vector search, LM Studio, Olama, and so on. So let me thank you all. I hope you learned something this afternoon about generative AI, about the examples we've shown. So, thank you, and if you're interested in our technical university, we have some information about Howest in general, and also about our Creative Tech and AI Bachelor. Please feel free, and thank you again, and maybe we see you in May or even in Belgium for a semester. Thank you very much.